Hello everybody, welcome to the testing part on the course on embedded system design, verification and test. So as you know that now we are actually talking about the advances of embedded system testing, and now in fact in this module we already discussed that we look at testing for advanced fault models, and then we look for built-in self-test and then fault tolerance. So already in the last lectures on this part we have already seen basically how real-time that is one of the main prerogative of embedded system nowadays is to meet the real-time requirements, and how advanced fault models like that is delay fault models are required for such cases and how they are tested basically. In this lecture we are going to see that what is something called built-in self-test of embedded systems, and in the next two lectures we will go for fault tolerance. So basically what do you mean by testing? What you have been learning in the first three lectures, that a device is manufactured, then we put it in the something called the automatic test equipment, we apply the patterns, test it and sell it to the market. Basically that is actually called chips are tested okay, are shipped to the customers with the assumption that they will not fail in their expected lifetime. This is actually called offline test. So what do you mean by offline? Chip is manufactured, we know some of the very important or good test patterns we have already generated by the ATPG algorithms, we put it in the tester, test it and ship it to the market. But whenever the embedded system hardware are becoming more complicated in the system, we are putting more and more system on chip on a single core, making NOCs out of them, or putting more and more transistors in a single die, and feature size is decreasing because of more advanced or lower level of submicron design technology. These are actually already discussed that they are making the probability of occurrence of faults more higher in case of such devices. So nowadays for such complex embedded systems or complex embedded hardware, you cannot assume that once the chip is manufactured and tested properly, it will do so in its lifetime. It is not guaranteed that way. So what is the next step we can do? The first step is called actually the offline test, because in this case it is offline verified, tested basically, and then you are selling it to the customer. He is putting into the board and he is testing and he is using it with the assumption that as it is already tested, so he should not have any problem in his lifetime. This is expected lifetime actually, but nowadays it does not hold. So a fault can even occur after it has been manufactured, properly tested, and it is being deployed in the system, and after 3 or 4 rounds of usage it may have a failure which is much before its expected lifetime. So nowadays what happens, how we can handle it? So basically what they do, they actually test the circuit every time it starts up. Now it is very difficult, say that I have a laptop and some of the ICs are already, embedded systems are already placed in that in the PDA or your mobile phone. Now before every startup of your rebooting of your system or switching on your mobile, you should test the chip. How is it possible? Can I bring the chip out of the mobile and put it in tester? No. But every time you have to test it, because that only can ensure you that basically that every time before it starts up, it tests itself, which actually that is called built-in self-test. I will tell you why it is called built-in, because before it starts its operation, it tests itself so that it gives you some kind of confidence that okay, now I am going to start my operation, I am normal basically. So that actually gives you more confidence that even if some failures which may occur after the deployment of the system can also be detected in that manner. And if that fault is detected, then it can flag off an error, or if there are redundant modules that can be switched on, and if there is no redundant module like in a home appliance like a mobile phone or a washing machine or a simple microwave controller, then it will give you an error, and it will also tell you that this chip is not working and some vendor will come and replace this chip. So what is built-in self-test? Built-in self-test is very similar to something like ATE-based testing, but in that case we do not have an equipment and you cannot take the chip out of it. So you will have an on-chip pattern generator and on-rip response analyzer. So in whatever test patterns you have generated, assume that we will put it in a memory and put it into the chip. And same thing, we will also have a golden response comparator which is happening in the ATE, can also be put on chip. So we are making a miniature ATE and putting in on chip. That is actually called built-in self-test mechanism. This is the pictorial diagram. So basically if you look at the pictorial diagram, we will basically have the circuit under test, and we have a hardware pattern generator. Here we are going to put all the test patterns which were generated in the ATPG algorithm, and then we will apply it to the cut under test, and then we can have a golden signature, that is the expected output, and we can do the comparison. Very simple story. Then you can ask me then why I should have a full lecture on built-in self-test. The story is not very simple. ATE is a physical equipment. It is a very huge memory, and it tests chips. You can erase the memory, a new set of chips comes and you can keep on repeating it, and the device is very big. Can I do something in the chip? If you are going to do it, the size of the test pattern generator and the size of the RAM where the expected responses are stored, and the comparator will be so large that it will be much larger than the cart itself. So it will be like killing a mosquito with a cannon. You are not allowed to do that. You will be able to do a test provided that this hardware pattern generator and this whole output response analyzer circuit very small compared to the cart. So that is what is the challenge. Principle is same, apply patterns, analyze response as in the offline test, but in built-in self-test, as everything is on chip, there are also some kind of hardware which will do it, so you have to keep it very small and limited in size. How can you make it smaller? First of all, you have to take care of very few limited test patterns which are really required for doing the test. That is first thing. Secondly, still you cannot have a full-fledged digital circuit to do it. Like for example, I can say you that I have to apply patterns say 1, 3, 7, 9, 12, 18 and so forth. So pattern I know. I can very easily generate a pattern generator circuit, which we have already done in second year digital design course. Like we implement next state, present state, next state, we can have, then we go for a Queen Maclance or Carnap based optimization, and we can simply design a digital circuit to generate the pattern. But assume that if it's a 512-bit input circuit, the pattern generator etc. will actually become a very large circuit. Similarly, if I have say 72 patterns, for which I want to test the circuit, because the 72 test patterns were very important for some perspective. Then the RAM should have the expected response for all the 72 input patterns. This will actually make the things very large. So the challenge of BIST is how I can make it very small in size, but still I have to generate the pattern sequence. Like as I told you, like maybe 7, 12, 18, 19, 27, say 108. These are the patterns. I have written in decimal. These are the patterns which have to be applied to the circuit for doing the test. I have to generate the same patterns. Maybe I can do it in a different order, because testing of first stacked fault or the second stacked fault and or vice versa does not have any impact. I can test the input fault first, I can test the output fault next, or I can interchange the position. So if this is a sequence of patterns required to test a circuit for all faults, I can also swap. I can make it 12, 7, 108. So I can easily change out the pattern sequence. So as we will discuss later, that if I can randomize or change the pattern sequence which does not affect testing, then the circuit for hardware test pattern generator will be very small compared to a deterministic pattern sequence generator. Like if I want to have absolute like 7, 8, 9, 18, 20, if I can slightly reorder them, then I will show you that you can have a very small test pattern generator circuit for that purpose, compared to the traditional digital design which we all know for our second year course. Secondly, this is how I can make the input response test pattern generator circuit lower in size. Secondly, if you look at the output response. So if I have say 72 input patterns, so if I store the response for all the 72 test patterns, the ROM size also will be very high, which is required for golden signal matching. So there is something called compaction. So you are not going to store the expected response for all the 72 patterns. In fact, you will club many of the output patterns together and then make a signature out of it. So I will tell you what do you mean by signature. Signature means a compaction. So it's a lossy compaction. So what do you mean by lossy? If I have not compacted that, then all faults would have been detected. But if I make a compaction, it's a lossy compaction. So maybe out of 72 patterns, we can make a batch of 8 patterns. I'm just taking an example. So 8 response I'll compact into 1 response. Again 8 response I'll compact into 1 response, and I'll make a golden signature out of it, and I'll do a match. But they will find that there are aliasing. That if I have not, the compaction was not there, then all faults would have been detected. But if I make a compaction, some faults will be missed. But still, we'll see that the area overhead of the ROM is very low. So what it gives me, obviously I cannot have as rigorous testing as in the AT, but still I will have a test which is basically much lower in quality and quantity compared to ATE based testing. But still I will get something in BIST. Instead of something is better than nothing. That is the philosophy. If I don't have a BIST, I cannot test my circuit before startup. But if I have a built circuit, even if it's a very small part of the original test which you are doing in offline ATE, but still that I can apply with a very lower hardware area overhead for the test pattern generator and the response analyzer with compaction. But still some level of confidence can be obtained if I have a BIST. So more reliability can be given. And research have shown that you can very easily have very good compaction scheme so that the aliasing is less. There is very low area overhead test pattern generation by something called linear feedback shift registers, as we will discuss in details today, which can give the random order patterns. Random order in the sense that the control of the patterns may not be as you desire, but all the patterns will be generated but in a different sequence. For given sequence, if you change the order, we will show that very low area overhead hardware test patterns generator can be designed, so that you can have a built-in self-test for maybe around 50% level of confidence compared to the ATE, but you can do the test. But researchers have shown that even with such low area overhead for the compaction based output and the LFSR based test pattern generation, still you can have a very smaller circuits will be there, but still you can have very good quality pattern generators, very good quality signatures can be generated even with compaction, which will still maintain the level of confidence of testing around 70% to 80%. So if I say that 100% is for ATE, at least 70 to 80% confidence can be even still obtained with such low overhead circuit. So for that a lot of researches has been done on how to compact the output, what are the different type of input sequences that can be generated, what are the very peculiar, very important test patterns that can be stored for duty testing. So all this we'll discuss basically. So the motivation is that built-in self-test can give you a certain more obviously more level of confidence compare means before for reliability, because the circuit is tested every time it starts up. But of course the testing cannot be as rigorous as offline test. Now this architecture tells you that as this is an on-chip hardware, so there is always a multiplexer which will be put in the front of the device. So if the circuit is normal, so I mean if the circuit is doing its normal operation, that is test mode is not there, the circuit is running, then the test controller will make this line as 0. So the normal inputs will be fed to the circuit and the output will be going to the primary output. Now if the test mode is 1, so test mode is 1 means the circuit is just about to start up, so you have to test the devices. So basically I will make the mask as 1, so normal inputs will not go into it, this one will the test patterns which are generated by this LFSR or the hardware test pattern generator will be fed to the cut, and basically the ROM will be activated and the output responses will be compacted, and there is a comparator which will tell you whether the circuit is properly operating or not. If it is operating properly, then basically the test mode will become 0, normal inputs will be coming and the circuit will be doing its normal operation. But if the error has been found out, then it will stop the chip and you have to replace the IC. That is what is the scheme of built-in self-test. Now this architecture is very simple. Now what we will concentrate on is how we can go for designing a very low area overhead hardware test pattern generation and how responses can be compacted so that we can have a very low area overhead. So what just as I told you, what are the different components, again they are written in this circuit. So hardware test pattern generator, basically what it does, it is simple, means it's a register, because if you generate patterns and there is of course is some kind of a counter, so n number of, if the n bit, if this is n bit input, so a n bit register will be there. But so these are the n bit registers. But these are some of the combinational circuits which actually feed these registers and also take the inputs back to this. This is a simple algorithm for a digital counter or a pattern generator. So these are the D-flops maybe. So the inputs to D-flops come from a combinational circuit, the outputs of the D-flop again go to the combinational circuit. So basically it's a counter, so if it is 0 0 0 0, present state is the present state is 0 0 0 0, the counter, the next state will be becoming 1 1 0 0 1. Let me just slightly clear it up and explain you. So this pattern generator is say the n bit pattern generation, let us take n as 2, so there will be 2 flip-flops. So there is the input to these D-flops, so this is actually your combinational cloud, and the outputs of the flip-flops are again feedback over here. So maybe the maybe the present state is 0 0, so it's a simple up counter. So the next this is the present state is 0 0, next state will be actually 0 1. So the next state will become 0 1, and this will be the present state, and the next state will be actually 2, so it will be 1 0, and then it will become basically 1 0, the next pattern will be here 1 1, and it will keep on going. Now if it's a predefined sequence like 1 7 9 15 etc., so this combinational circuit will start becoming larger. So you cannot do a magic, you cannot read, if the n bit counter or n bit sequence generator, the number of flip-flops will be, you cannot do any magic over there. What role it is played basically, how can we reduce this combinational circuit? If you look back your digital design fundamentals, you will find out that this size is not very less. So if it's a 512 bit counter is there, the size of this one will be extremely large. So what role people plays, or the intelligent hardware design techniques play, is to reduce this combinational circuit, because if it's the n bit input is there, by no means you can actually make this input the counter or this one have less than n bit flip-flops. That is not possible. So what is the hardware test pattern generator? Basically it is nothing. So it will have a state register of n bits. So but as the test pattern generator circuit is a circuit, not an equipment, its area is limited, as I already told you. So storing and then generating the test patterns obtained by ATPG algorithm on the card using the hardware test pattern generator is not feasible. So therefore it cannot be a predefined counter. So basically instead the test pattern generator is basically a type of a register which generates random patterns. So that pattern sequence I am not containing. As I told you, if the first test pattern is tested last, the first fault is tested last, and the last fault is tested first, I have no problem. Faults will be tested. So basically the test pattern sequence I don't control. but the number of test patterns I control. Like for example, as I told you, 1, 2, 7, 9, 12, say are the test patterns. Okay, it may be detecting the first fault, the second fault, third fault. Maybe I have numbered the faults in numbers. But this I have no problem if I start with 7, then with 12, then with 9, then with 2, and then 9. I have no problem in that. So as we'll show you that there is something called linear feedback shift register based pattern generators, where if you randomize this order, the size of this combinational circuit becomes very, very less. So basically the main emphasis of the register design has to have low area, yet generate as many possible patterns in the flip-flops. So because I mean, as I have given here, I have given a stray example like say 1, 2, 7, 9, 12. So this test pattern, the state space is bit sparse, but it may not be the case. It may be 1, 2, 3, 4, maybe one gap I will have 6, maybe 7. So these are all the patterns which is required for a 3-bit counter. So maybe only one is remaining, that is actually say 1, 2, 3, this 5 is basically remaining, which I don't require as a test pattern. So basically my main job here will be to reduce this combinational circuit area, but still generate as many as patterns possible from 0 to 2 to the power n minus 1, full range. And in fact, luckily the theory has been established that there exist circuits with very, very low area over it, which can generate patterns from 2 to the power n minus 1. In fact, I will show you 0 is not possible to be generated. So we have patterns basically from 1 to 2 to the power n minus 1, almost full range patterns can be generated from 1 to 2 to the power, very low area over it, but this pattern sequence cannot be controlled. Maybe 2 to the power n minus 1 will come over here first, maybe after that 1, then 9, then 7, and so forth. So that is what is the hardware test pattern generator. Input marks, as I already told you, it tells that when the system is operating in a normal operation, PI should come in, primary input should come in. In case of test, the patterns from the ATP, that is hardware pattern generator, should come in. Output response compactor, as I have already told you, that for each individual test patterns, if I store the expected responses in the RAM, so it will be very large. So basically we compact the response, and it's a lossy compaction. So that means out of say 100 responses, we will be making bunches of 10. So every 10, 10, 10, 10, or some type of algorithm I can use which can compact the responses and make a 1-bit or 8-bit or some X number of bit representation for these 10 output responses, and it will be represented by single bit or 2 bits, whatever you can decide. But that is a lossy compaction, but still we have to do it for minimizing the area of it. So that is actually called output response compactor. Then ROM, which actually stores the respected response of the compacted input sequence, or the compaction, means for all 10 outputs, if I explicitly store the responses, ROM size will be large. So I have make a compaction. So they say input pattern 1, 2, 7, 9, 12. I have made a club. So this is all the output responses, maybe 1, 0, 7, 0, 1, 9, 0, 1, 2, 3. These are outputs expected for these are these inputs. Like say input size, I say 1, 2, 7, 9. Maybe these are the 4 inputs, and maybe the output expected in this case is 0, 1, 0, 0. Say this is again 1, 1, maybe 0, 0. So this for every 4 input sequences, the output sequence I will make it as a single response, as I am compacting. So these 4 responses I will compact, and maybe I will represent it by 2-bit or 1-bit. Some algorithms are there, as we will discuss. So but all the output explicitly I will not store the expected responses. Basically I will make a compaction and store it into the RAM in a less bit odd number of bits. Like here in this case 1, 2, 3, 4, 5, 6, 7, 8. 8 bits are required to do this. But if I compact it, maybe I will be representing by 2 bits, maybe 0, 0. How I am getting 0, 0 from all this, we will discuss that algorithm later. So I will represent it in only 2 bits or maybe 1 bit or even 3 bit also I can keep it, but with less than 8 bits, and I will put it into the ROM. So basically now whenever I am getting all the responses for this pattern like 1, 2, 7, 8, this one will be compacted and compared with the, and that value will be compared with the expected compacted response. Like for 1, 2, 9, 7 and 9 as input vectors, the output respected are this, this, this and this. So explicitly I will not store in the RAM these 4 values. I will make a compaction, maybe there is called a signature, which will be stored in the ROM with less number of bits, and whenever the circuit under test will be applied with these patterns, these outputs will be again compacted and compared with the expected compacted response. So comparator compares the compacted outputs with the expected compacted response. That is what is actually the RAM stores. So comparator is very simple. It will compare the expected compacted cut response with the golden signature from the ROM. So basically this is your golden signature. That is the expected compacted response. And basically these are the cut outputs. They are again compacted and matched with the golden signature. There is something called test controller. It basically decides when to start the BIST, when to stop the BIST, if there is a fault, what it should do. So it's a controlling generation circuit. Generally what it does, if the device has to be tested or this device is starting up, it will actually make the mask in such a way that random patterns from, the patterns from the hardware generator is applied. This is the control patterns and testing is done. And when after that test is okay, it will switch the input so that inputs from the normal primary inputs come to the circuit. So that is one of the job of the test controller. If any fault occurs, it will flag off that this device is having a fault and something else can be actually done over this. So these are actually all the components I have described for this hardware. Now basically what we will do, we are now going to look in details about the hardware test pattern generator, how it has to be designed, how it has to be tested, basically how it is such a miniature version. So even it is generating all the possible patterns for a given n bit number, n bit input bus, or if the number of input bits are n, it is generating a large sample space. Like for example, we should not call it 0, it cannot generate from all zeros. That is the only thing that is not possible to be generated. It generally generates all patterns or very huge number of patterns from 1 to 2 to the power n minus 1, if n is the number of basically your input bit bus size, right? So we will see this is very interesting to see that even just with a single modification that I can randomize the input patterns, we will show that a very less area overhead pattern generator can be designed. So now we are going to look how such things can be designed, but there are typically two different type of ways to do it, which we call standard linear feedback shift register or modular feedback shift register. These are the two specialized register design which enables you to get a very huge state space of inputs from 1 to the power n minus 1. Now we will be looking at that. So what we are trying to look at is that how can we make that register size area small for that combinational part, but still you have to generate a large spectrum of the input space, that is from 0 to the power n minus 1, but as we will see 0 is not possible to be generated. Now let us look at the circuit structure which makes this magic. So there is one circuit structure which is called standard linear feedback shift register. So in this case, if you will see that basically if I try to zoom it for you, so you will see that basically what happens. So there is a sequence of flops 1, 2, 3, 4 and up to x naught, and everybody is connected. Everybody is feeding the direct flip flop directly to the next, but only one, the MSB flip flop, is connected from the output of the LSB flip flop, but it is not directly connected as in the case of others, like these are the ordinary connections, but here is a feedback connection, and in the feedback you will have lot of XOR gates, like this one here. There can be an XOR gate which is actually the output of x1 XOR with the output x0. Even output of x0 to x3 x4, everything can be there or it may not be there. What I mean to say is, this is the proper structure, everything will be a direct connection, simple shift register, but the output of the LSB register flip flop to the MSB flip flop, there is a feedback chain, and this output will be depending on this one XOR this one XOR this one XOR this one, but everywhere you may not have a XOR gate. So depending on where you place the XOR gate and where you do not place the XOR gate, the sequence of patterns or the output spectrum will depend. Here of course you can very easily feel that all zeros cannot be generated. Like if I put a all 0 over here, so what is going to happen? Everywhere the 0 will shift, and if I put any number of XOR gates, XOR with zeros, always is a 0. So it will be a 0 and it will be locked at 0. So any LFSRs, whether it's modular or standard, if 0 is basically given as the initial seed, it is going to lock. So except all zeros, huge spectrum of inputs can be generated, and what sequence, what pattern depends on where and how you place this XOR gates. So actually there are a lot of mathematics from coding theory which is involved, which predicts that given if I put an XOR gate here and I drop it here, what is the pattern sequence generated, what is the spectrum. So there is a huge amount of mathematical logic and theory which exists in coding theory literature, which tells you how you can orient these XOR gates to get this output patterns in a prerequisite fashion, or I mean in a randomized fashion, but still the input spectrum. Randomized in the sense that for a given sequence of or type of XOR gates, and basically for a given type f in length, what is the sequence pattern and what are basically which are the missed patterns and which are the patterns which is covered from 1 to the power n minus 1 depends on how you select these XOR gates. But that theory I am not going to go in because the proofs etc. are quite involved. Only from the and for most of the test perspective, there is something called basically which we will see. The name is characteristics, basically what I actually call primitive polynomial, which is the term. So basically will just keep the term in mind for the time being, that the theory exists which tells you that is the primitive polynomial, the terminology which tells you where to put these XOR gates and where not to put the XOR gates. If there is no XOR gates, therefore in that case it will not depend. Like if I don't put an XOR gate over here, so it will be directly connected over here. So this flip flop will be just be a shifting flip flop. So and the way the flip flops are connected will define a mathematical function which is called primitive polynomial. So, for a given n and a given the primitive polynomial, that primitive polynomial will tell you what are the input sequence generated and whether you can generate the entire sequence from 1 to 2 to the power n minus 1. So, depending on your requirement, you can select a primitive polynomial and accordingly you can build this circuit. So, why the primitive polynomial works, that why only for this primitive polynomial you can generate an exhaustive set of patterns, because more or less our job is to require to generate as many patterns as possible, because then in your case the coverage will be higher. So, why such primitive polynomials only generate such kind of exhaustive pattern set is a theoretically involved subject. You can go to any coding theory book on linear feedback shift registers, you can know the theory behind that. But here what is our test engineers will do, they will given us a value of n, then we will go to the literature and find out the primitive polynomials for that, accordingly design the LFSR and it will generate the huge spectrum of numbers. So, we will go by this. So, how it is represented? So, in this way it is represented by a matrix. This is a matrix which represents it. So, here basically it is a matrix with all diagonals as 1. This column everything is 0, there is a 1 over here, and the last row is h1, h2, h3, hn minus 1 and h minus 2, that is the h's. So, what are the h's? H's are basically these values. So, if you are putting a flip flop in for this flip flop, that corresponding h will be 1, and if there is no flip flop in this, sorry, no XOR gate in that case, like for example if this XOR gate is not there, then this is not there, it is a direct feedback. So, in this case h1 will be equal to 0. So, whether I am putting an XOR gate for the corresponding flip flop or not, basically these h values will remain, right, and this is the column. So, all zeros and a single 1, and this is the matrix. So, this is what this actually represents this LFSR. Now, how? We will explain this. Like for example, if you look at it, so for all cases like x0 is equal to x1, next stage x1 is equal to x2, xn minus 2 is equal to x1. So, how it happens? So, if you look at what is the value of x0 t plus 1. So, in this case basically if you look at, this is multiplied with this is multiplied with this and so forth, and all others are 0. So, x0 t minus 1 will be equal to x1 of t. Similarly, if you look at x1 t plus 1. So, in this case if you look at, so this one is multiplied by this one is multiplied by this one will be something multiplied by this. So, this one will be actually x1, this one will be actually x2 of t. So, that way. So, similarly you can easily calculate that basically this one will also be dependent, basically this one will be dependent on this and so forth. So, for all the flip flops from x0 to xn minus 2 like this will be just depending on the previous flops, just depending on the previous flop values. So, which is described by this part. Now, very interesting is how xn minus 1, that is the MSB flip flop decide. It is a function of this. So, always if no XOR gates are there, still there will be a feedback over there. So, it is basically equal to x n minus 1, the MSB flip flop is equal to x0 t. Now, if x h is equal to a 1. So, if x is equal to a 1, that means there is a flip flop over here, sorry XOR gate is over here. So, it will be again XORed with this gate. So, in this case h1 is multiplied by this one. So, it will be actually equal to XOR x0 equal to t, then it will be XOR with x1 of t, again XOR with x2 of t and so forth, if these corresponding bits, sorry, if these corresponding bits are 1. So, if everything is a 1, then it will be XOR with x0, x1, x2, x3. So, if all the flip flops are here as in this picture, this one will be an XOR of the output of all the flip flops. So, this row basically tells you what is the input driving for this. So, just with a little careful looking at it, you will be very easy to find out how this linear feedback shift register is represented by this matrix, right. So, in now basically this matrix can be represented as a characteristic polynomial like this. So, I am zooming it for you. So, it is just a simple way of writing x1 square n minus 1 and xn. So, this actually is a mathematical representation, the characteristic polynomial representation of the matrix. So, if you are not putting a XOR gate in the respective position, such h's will be actually becoming 0. So, these terms will be going out. Example, that is better. So, if you look at, this is a LFSR, right. So, in this case 3 bits. So, the matrix also with 3 cross 3. So, this part is a matrix with all the diagonal elements as 1. So, that is not a problem, this is a standard. Now, if you look at, so in this case there is only one flip flop which is at the output of x2, or here actually there is no flip flop over here. So, if you look at, this corresponds to h1. So this is 0, this corresponds to H2, so it's a 1 over here. So this 2 represents this flip flop, that there is a XOR gate over here, and this 0 represents there is no XOR gate over here. Now look at what is the value of x naught. So x naught t plus 1 is actually equal to x1. So this one is very simple. Similarly, if I study the value of x1 at t, it is also nothing but the value of x naught of t. Now x2 of t. Now important is what is the value of this one, this guy. So it is basically equal to x naught, this one, second bit is 0, XOR with this one, because these are 1. So basically you can see the output of this is XOR of this one and XOR of this one. So basically this circuit is represented by this, and the polynomial is 1 x square x cube. So 1 and x cube will be anyway there, but only x square is there, x is term, the term is missing because this is not filled by a XOR gate. So I can put XOR gate here also, all the 4 combinations I can use. Basically no XOR gate is not the combination to be used. These are all locking 0 sequence. Either I can also put a XOR gate over here, I can remove this, and I can also put a XOR gate over here. So this is how I can basically do it. Importantly, what it can generate. So first there is something called a seed. First you have to put a seed. Again, as I told you, can easily find out that if I put the seed as 0 0 0, so you can see that it will be again a 0 because XOR 0, it will be locked. So all zeros cannot be generated by any kind of LFSRs, but that is not a problem. Basically, if you say that I have to put a all 0 as a test pattern, then what you can do is that you can make all these resets, first generate all these 0 patterns, and then basically generate a seed pattern. So how can I generate the seed pattern? The seed pattern is saying 1 0 0. So these are again reset, but it is a first bit x naught is a 1, so you can make it as a set. After that you need not put any set and reset, and automatically these patterns will be generated. So let us see how it is generated. So in this case it is saying it's a 1, it's a 0, and it's a 0. So the next input will be a basically if you look at, so x naught is 0. So next, this is the first sequence. So x naught is a 1 and these are 0 0. The next batch, what is going to happen? This x1 is going to become x naught, right? Then x2 will become basically x1 in the next case. And what about this? This one is actually defined by this XOR gate. So it is a 1 and a 0, so XOR is a 1, so you are going to get the value as 1. Similarly, you can find out that this is the pattern sequence which will be generated one after another. And if you look at it, what is the sequence? It is maybe I call it as 0, 4, 6, 7, maybe it is 3, 5, 2, 4, 1, something like that. So it is actually a 4. Yeah, and after that basically this is what is being generated. So again it's a repetition. So it's a 4. It's a 4. Then I call it a 1. So this after, see, you have to see that after this one again the pattern will start repeating. So what basically I have found out, how many different patterns are generated. So I started with this, and this is what is a repetition. This one, if I call it as a 4, if I call it the LSB, so it's a 4, and this is basically a 1. So in this case 1 and 4. So basically I am generating all patterns up to this. So what are the patterns I have generated? So what are the patterns I have generated? Because from here the repetition starts. So it is a 4, 1, 6, 7, 3 and 5. So 1, 2, 3, 4, 5, 6. So 6 patterns are generated by this sequence. 1, 2, 3, 4, 5, 6 and 7. So 2 to the power n minus 1. Just by using a simple XOR gate I can generate it. But again the pattern sequence you can see it is 4, 1, 3, 7, 5, right? Sorry, 3, 5, 2. So I have no control in this sequence. So with this simple XOR gate, I can generate almost entire spectrum for a 3-bit case. So only all zeros are not generated, except that all other patterns are generated, right? So it's very interesting. But if I want a sequence something like that 1, 3, 4, 7, say in ascending order. So in that case, it's an up counter or a particular pattern counter. So in that case, you cannot do it with a simple XOR gate. It will be quite large circuit. Just by looking at the digital design fundamentals, we can find out how to design such kind of interesting counters, like up and down counters, particular sequence generator. So it is never a single gate, it's a large bunch of gates. So for 3 bits, only one gate is doing it. Very interestingly, in case of LFSRs, as we will see, even with the very high increase in the number of bit size, bit width, the number of XOR gates required will be not very high. But if you are going for predetermined pattern generator sequence, by using digital design, final state machine based optimization sequence, it's a very, very large hardware. Maybe hundreds of gates will be required for a 32-bit input or something like that. So here the saving is huge. So again I am re-emphasizing that why this LFSR is very good for BIST, because it will, for most of the cases, like if you are using a primitive polynomial, entire sequence is generally generated from 1 to 2 to the power n minus 1, but the order may be slightly randomized. But still I have no problem because faults can be tested in any order. But the gate size in this case is only one XOR gate. But if you are going to generate a predefined sequence, this combinational cloud is going to be quite high. So that is actually the big gain for LFSRs in BIST, that even if it's a large number of bits also, the number of XOR gates will be only very right. So that is what is the boon. Now some people had a problem over here in such kind of standard LFSRs because they complained that you see this one is comprising of so many XOR gate sequence. If it is a 32-bit, there may be in the worst case 32-bit input levels. So it may be a very slow design because because the delay of the XOR gate, that can happen. So then people have shown that we can also design another kind of LFSRs which are called modular LFSRs, where this delay is reduced but same characteristics of generating a huge spectrum of inputs are possible with a very low area overhead. So in this case what they are doing, in this case the first flip flop is feeding the last flip flop directly, but instead of in the standard LFSRs we were having a connection like this, but in this case it is not like that. You can put a feed a XOR gate here, or you may not put it. So the control comes over here. So these are called a modular LFSR. Standard LFSRs means here these were all directly connected and we are putting XOR gates in the top. But in this case it's slightly different. We are going a reverse about connection. We are doing basically this. So in this case, see, at between any two flip flops only there is a single XOR gate or no XOR gate. So it's a more faster design. Again, it is extremely just a mirror map. I am not going to deal in more details. You can just look at the slides for that. Same characteristics will be generated, but in this case just a dual of it. So here you will get this square matrix over here, and in this case basically this is the all ones HS, whether you are putting XOR gate or not, and so this column will determine the basically your this value for the next flop and so forth. So this is whatever I have discussed for standard LFSRs also hold for basically the modular LFSRs, only it's some kind of a mirror image like that. So this is the matrix representation for this. Then there will also be a similarly characteristics polynomial, and other theories is more or less similar. So you can just look over the slides and you will get a feeling. So in this case is also an example of a modular LFSR, in which case also now they have taken a 4-bit number. So if you are counting, it is 1, 2, 3, 4, 5, 6, 7. This is the seed. So the seed is repeating over here. So if you look at it, it's a 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So 15 numbers are generated, entire spectrum 2 to the power 4 minus 1, because zeros are not generated. So even just by putting a single XOR gate, you are able to generate the entire spectrum for 4-bit input cases. The characteristics polynomial is this. Basically 1 and 4 will always be there. There is only one XOR gate, so the XOR factor is there. So initial values are this is the seed vectors, and this can be easily generated. You can easily verify by this slide. So what here I am emphasizing that for 3 bits, 4 bits, 5 bits, similarly it can be shown that with very few XOR gates you can generate the entire spectrum of inputs. But if you are going to make a controlled generation, just like we do in digital design, finite state machine generation, it's a huge circuit that cannot be used in BIST. But LFSRs are very well suited for BIST. Okay, now the question arises, can any LFSR would generate these patterns? As I told you, it's no. Only a few characteristics polynomial, the LFSR is maximal length, that is entire spectrum is generated. They are called primitive polynomials. This is actually the paper. So here a lot of proofs are presented that what are the primitive polynomials, for what length you should select, what is the area impact on that, because based on the polynomial size or polynomial type you have to put the XOR gates, correct? So if you are putting such kind of XOR gates, then the size may vary. So like for example in this case the primitive polynomial, you can directly find out that I require a single XOR gate. But if it is say x1 plus x square plus x cube plus x4. So for this bit and this one, no XOR gates are required, but here 2 XOR gates will be required. If it is a primitive polynomial, you know that 2 XOR gates are required, but it may be generating the entire spectrum. Just I was giving an example. So just by your requirement, you look at the characteristics polynomial available for different ends and you select and do it. So test engineers basically do not that way directly involved in the theoretical proofs, rather they know the theory works. So you select the required means ATPG vectors, which you know which will be generated by this LFSR. You can select a primitive polynomial, and for certain cases if you do not require the entire spectrum of values to be generated, maybe only 4 or 5 different patterns to be generated, then accordingly you can put the XOR gate and design the LFSRs. But the key thing is that the size is very less, only a few XOR gates will do the trick. That is why LFSRs have become a boon for BIST. So I can also say that if LFSRs were not there, BIST was a very difficult problem, because I require a very low area overhead test pattern generator, and which is being possible by LFSRs. So your problem of input generation is solved. So you have a LFSR, it will generate the maximum spectrum of inputs and you are happy with it. Now what about the output? Because LFSRs, they are generating the entire spectrum of inputs for you in a random fashion. Then for each pattern, should I store the output response? I can do it, but in that case your expected signature, that is ROM, where actually the values has to be stored for the golden outputs required, that is the expected output of the cut, will be very, very large. So what we do is basically we go for compaction. That is, we will make a block of some of the input outputs, or even all the outputs we can make a block. That is, given output, expected output sequence, we make some kind of a compaction arrangements and we represent by 1 or 2 bits in a very compact manner. That is called a compaction, but it's a lossy compaction. Lossy compaction means for some of the cases the errors may be, faults may be masked. But still, to make the area optimization, we have to do it, and also theory exists that there are a lot of good compaction algorithms or techniques available where the aliasing is very, very low. We are not going into more depth on this, but rather we try to see very two simple type of compactions and see what is the aliasing and how it can be avoided. So very two simple compactions we will look at this lecture, that is called the one count and transition count. One count means if they say the output sequence is, as I told you, maybe 0 0 0 1 1 1 1 0, something like that, then we will be counting how many ones are there. There is 1 4, so we will store the value of 4. That is, in this whole expected output values, the number of ones are 4. So you will just count the number of ones. So if some fault happens, like in which case this is made as a 0 and this is made as a basically, and this is made as a 1, your faults will be aliased, because you are just counting the number of ones. 2 faults occur which cancel each out, then it is gone. So another type of is called the transition value. So transition value means how many basically transition happens. So for example, if the input output sequence is 0 1, I am assuming a 1 bit as output, 0 0 0. So what is the transition? One transition and another transition. So you will be maintaining the transition count as 2. But also you can find out that this can also have some aliasing effects, like if something balances out, maybe it becomes a 0 and this becomes a 1. So faults are there, but the transition count will be 2 and errors will not be detected. But we will see for many of the cases, however, even such simple compactions can detect the errors. But there are more complicated testing, again based on LFSR, which actually can minimize the compaction like anything, but the theories are more involved, we will not go into that. If you are interested, you can find out the entire literature on LFSRs, on built-in self-test, or basically in coding theory, you will find out the entire spectrum of literature on that. But we are going to see today simple compaction techniques and what it results, we are going to look at it. So for example, this is a simple circuit which we are taking, and we are taking a simple stacked 1 fault over here, and we are taking this BIST circuit and we are generating these patterns. And our the compaction technique we are taking is counting the number of ones. So you are applying these patterns, you will find out that the number of ones are 1. Now you can also zoom it for your help. So I am doing it. So I have zoomed, this is the input, and also putting a stacked 1 over here. And if you do the operation, you will find that the number of ones are 2 at the output. Basically for this input sequence, so this is the input sequence generated by this LFSR already, which we have designed. We are applying patterns to that, and this is the output, and for a fault you will see that the number of ones has become a 2. So the compaction was, in this case the expected answer is a 1. I am not going to represent explicitly all the values in the ROM, only I will say that for this this pattern set I am going to store 1 as the expected response in the ROM. So if the stacked fault happens over here, the number of ones will be 2, so this error will be, or this fault will be detected. But there can be a lot of aliasing cases also. In this case it works. So this is basically compaction. Instead of storing this value explicitly as the expected response and comparing bit by bit, we are not going to do it. Rather, for this block we are going to take the total number of ones here and store that as in the ROM as a golden signature. That is what actually I have written in this slide. You can easily read and get what I have told to you. Another example. So another circuit I have taken. Again same input patterns I am giving over here. These are the patterns and this is the output. Number of ones are 2 for this circuit also. Again here I am going to take a stacked 1 fault. So this is going over here. So this is 1 and the outputs will be all zeros if you compare the number of this, what is the output. So surprisingly in this case the number of ones are also 2. So if you look at it, why the aliasing has happened? So it's simple if you look at it. So if somehow I could have managed this, so you can look at it. So in this case this is 1 bit, the MSB has been flipped over here. If you look at this 1 bit flipped from 0 to 1, and on the contrary this is going from 1 to 0. So they are balancing each other. So the number of ones still remains 2, but still there is a fault, because the first bit can itself tell you that there is a fault which has occurred, but it will not be captured because you are not explicitly storing the full vector, right? Then you can tell me which is a better compaction method. In fact it depends on size, circuits to circuits. So from here it may appear that counting number of ones would have been is a very bad solution. We can take something else like transition count. Anyway, this is the story for this slide. Now here, so transition count. So I am just going to give you a story about transition count. So from here it may appear that from there it may appear that number of ones counting is bad, it is aliasing. So let us see about the transition count. I am taking the old circuit which we have considered previously. So in this case, so this is the normal, this is the input sequence from the LFSR, this is the what is the output. So you can see the number of transitions count will be 2, 1 and 2. Again, all stacked ones, this is a stacked 1 value, you will see that this is what is the output. Here also this transition count is a 2, because 0, 1, then no transition 2. So in this case, counting ones, because it is 1 1, there is 2 ones, it could have been detected by the counting 1 based aliasing, but transition count it fails in this case. Then I can I say that transition count is a bad example or a bad way of handling this type of errors or the bad compaction? The answer is no. If you take this one where the number of 1 counts failed, here it will succeed. So here if you are looking at it, so we know that this is the normal one, the transition count is 2. This is the other second circuit you are using. But here the error is, you know that this is what is the error output for this stacked fault. So in this case, if you look at the transition count is 1, then again 2 and then 3. So the transition count is 3. So in this circuit, the transition count based compaction works. So what it tells basically that for a given circuit and a given fault, which aliasing method will work better, it depends. So here what I have tried to show you that, but these are very not very good kind of aliasing techniques. As I told you, a lot of theories exist for LFSR based techniques for basically compaction which give very low aliasing within very low area, but they are more theory intensive. So I have not covered in this lecture, but as a future or part or additional you can read over there. But what I have shown you basically is that compaction can actually go for fault detection with of course a compromise, but the area overhead is very less, because here you just want to require the count. So it's a log complexity which comes in, and here basically obviously same thing when you are going for counts, so it's a log complexity, either transition count or the number of 1 count, so it's a log complexity, that if the variable size is n, only log 2n bits are required to store it. So the area for the ROM is lowered, but still there can be some kind of a compaction error. There are lot of theory exists which tries to modify this so that they can get good compaction algorithms, but again area is very important. I cannot have a very large area and explicitly store all of them and get a 0 compaction and I can get very good results. That is not actually allowed in BIST, because in BIST everything is inside the chip and you cannot make your tester circuit more large than the circuit itself. Then it can happen that if your tester circuit is much larger than your cart itself, then the probability of occurrence of faults in such circuits also increases. Because what is the theory or the statistics, it says that if the circuit is large, then the probability of occurrence of faults also in this case becomes larger, right? But if you have a very smaller circuit, then you can properly design it with much more spacing between the vias and the wires, and you can have slightly less probability of faults there. So certain tweaks we can do, or even if you are not doing any tweaks also, a smaller circuit is going to have less probability of errors. So therefore we want to keep the circuit of the tester much smaller, for both for lower probability of errors as well as for the cost, because nobody is going to pay you for the test, everybody is going to pay you for the circuit, functional circuit. So you want to bring it smaller. So therefore, basically what we have seen in class, that built-in set is very important to boost the confidence of the working of the circuit. But for that is very important is that we should have a very low area overhead pattern generator and very low area overhead response analyzer. So pattern generator is very good, well solved by LFSRs, because with a very little XOR gate into business you can generate the entire spectrum of inputs. For the outputs, what is the problem? You have to go for compaction. So here actually a lot of aliasing happens and lot of theoretical works are done so that you can get a low area overhead using LFSRs, etc. But the compaction is lower. So anyway, that we are not going into details in this module, because it's a coverage of design, verification and test. So you can look at very dedicated embedded system testing courses which deals more on this. So with this we come to the end of the lecture on BIST. In the next 2 lectures we are going to look at fault tolerance. BIST happens at the startup of the circuit. Offline test happens when the chip is manufactured, but if some problem happens when the chip is doing its normal operation, then who is going to solve it? There is some testing which tests the circuit itself while it is doing its normal operation. That is called concurrent testing or online testing, which is mainly required for fault tolerance. The next 2 lectures will be dedicated to that. Thank you.